Hello, my name is David Lee Jr. This is my Lab 3 for Physics 2, focus on circuits. Just looking at table contents, we'll be looking at first the intro and the purpose of the experiment, then we'll talk about some fundamental principles, talk about the summary of the experiment, some of the procedures, the experiment details, and then finally a discussion and conclusion. The overall purpose of this experiment is to utilize the principles of energy conservation to make informed predictions on circuit behavior, and then evaluate those predictions by constructing a model and using multimeters to measure current and voltage. There's three main fundamental concepts used in this experiment. The first one is Ohm's law, which is voltage is equal to current times resistance, capacitance, and loop and node rules. The loop and node rules. The loop rule is sum of all potential differences around a loop is zero, and node is the sum of currents into a node equals the current out. Here's a preview of results plus some initial observations. The current decreases over time through a capacitor. Voltmeters have high resistance, ammeters have low resistance, and when an ammeter is in parallel to a resistor, the current is 0.06 amps. Initial conditions, now this is a simulation, so the system is the circuit, surroundings, everything else, and again, because it's a simulation, we can assume the resistance of wires and the ammeter is negligible. Part 1 of the experiment, key components are two 1.5 volt batteries, two resistors, and two ammeters. According to the loop rule, we can assume that I1 and I2 are equal. The resistor is equal to 147 amps. And Ohm's law, which is again current divided by resistance, gives us an expected value or an estimated value of 0.0204 amps. The model showed 0.02, so that's very close. The current did not change when the ammeter's direction was reversed, and with the voltmeter added, the current is 0 with a voltage of 3 volts. Here's a continued part of part 1 of the experiment. We were asked to evaluate the current at certain locations using the voltmeter. From AB, which is the gap between the two batteries, is negative 3 volts. Then from BC is 0. From CD, which is the first resistor, is negative 0.96 volts. From DE is 0 again. And then when you get to the next resistor, it's negative 2.04 volts. And the remaining parts of the circuit all add up to 0, which gives us a net current of 0 volts. Here is the graph to show the change in voltage over time as the current progresses throughout the circuit. We are also asked to calculate the resistance for the various components in the circuit. Here I use Ohm's law, so you can see those calculations here. Part 2 was focused on RC circuits. So for this, we had to use a 9-volt battery, a 20 farads capacitor, and a 30 ohm light bulb, and basically measure and observe how the current changed with the battery attached and with the battery not attached. So with the battery attached, the current charges over time and the bulb dims. Now with the battery removed, the capacitor does actually discharge, but the bulb also dims as well. We were also asked to look at the changes in how long it takes the light bulb to charge, at least when it comes to a different resistance. So it pretty much doubled as the resistance doubled. As you can see, it took 4.42 seconds for the 10 ohm light bulb to charge, 7.02 to discharge, and around 10 to 11 to charge for the 20 ohms, and 15.5 to discharge for the 20. Then, using the components as I initially said, which is the 30 ohm bulb and a 9-volt battery, we plotted the voltage for 20 seconds using LNV, which gave a slope of negative 0.1668 seconds. And then using the formula provided, which is negative 1 divided by the slope, which we've calculated using Google Sheets, we got 5.995 ohms farads, which is very close to our expected value of resistance times current, which is equal to 6. So there's not really many possible areas for this experiment, given that we use a simulation, so pretty much the only way that there could have been errors and inconsistencies with the stopwatch, possibly not stopping at the exact time that it was 1 second, things like that. What if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So actual ammeters have some resistance, which would have increased the total resistance in the circuit, thus overall decreasing the current. What if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Will this prediction happen in real life? So ideally, no resistor would indicate no resistance at all in the current, and the battery would then be allowed to charge nearly spontaneously, if not instantly. And in reality, however, nearly all components and circuits have at least some resistance, which would then cause the current to not immediately charge the capacitor. Thank you for watching.